Okay, the following are the readings assigned for Lecture 6, and I just want to note that I took a few days off of recording and uploading these videos because I try to understand what I'm reading before I read it and record it, and I didn't really understand the concept of derivatives, and that's discussed in this section, and so it took me a few days learning about derivatives before I felt truly a little, at least mostly comfortable explaining it. And then I noticed that there's a footnote at the end of this section that says, if you've not encountered functions and derivatives before, this section will be a bit slow sledding for you. But don't worry about it, it's not that important. It's a cool algorithm. We'll come back to it maybe later at some point, but it's not important to not understand derivatives right now. So 3.4, Newton, Raphson. The most commonly used approximation algorithm is usually attributed to Isaac Newton. It is typically called Newton's method, but is sometimes referred to as the Newton-Raphson method. It can be used to find the real roots of many functions, but we will look at it only in the context of finding the real roots of a polynomial with one variable. The generalization to polynomials with multiple variables is straightforward, both mathematically and algorithmically. A polynomial with one variable, by convention we write the variable as x, is either 0 or the sum of a finite number of non-zero terms, e.g. 3x squared plus 2x plus 3. Each term, e.g. 3x squared, consists of a constant, the coefficient of the term, 3 in this case, multiplied by the variable, x in this case, raised to a non-negative integer exponent, 2 in this case. The exponent in a term is called the degree of that term. The degree of a polynomial is the largest degree of any single term. Some examples are 3, degree 0, 2.5x plus 12, degree 1, and 3x squared, degree 2. If p is a polynomial and r a real number, we will write p of r to stand for the value of the polynomial when x equals r. A root of the polynomial p is a solution to the equation p equals 0. That is, an r such that the p of r is equal to 0. So, for example, the problem of finding an approximation to the square root of 24 can be formulated as finding an x such that x squared minus 24 is pretty close to 0, you see. Again, if you don't worry. Newton proved a theorem that implies that if a value, call it guess, is an approximation to a root of a polynomial, then guess minus the p of guess over the derivative of the p of guess, where p tick is the first derivative of p, is a better approximation than guess on its own. The first derivative of a function, f of x, can be thought of as expressing how the value of the function of x changes with respect to changes in x. That is, how does the output of this function of x change in respect to the input changing, x itself changing. For example, the first derivative of a constant is 0, because the value of a constant doesn't change. For any term c times x to the p power, the first derivative of that term is c times p times x to the p minus 1th power. So the first derivative of a polynomial of the form c1 times x to the p power plus c2 times x to the p minus 1 power plus so on and so forth plus cx plus k is c1 times p times x to the p minus 1 power plus c2 times p minus 1 times x to the p minus 2nd power plus so on and so forth plus c. Again, just breathe. It's okay. It will be okay. I know that doesn't make any fucking sense at all. To find the square root of a number, say k, we need to find a value x such that x squared minus k equals 0. The first derivative of this polynomial is simply 2 times x. Therefore, we know, speak for yourself, that we can improve on the current guess by choosing as our next guess, guess minus guess 2 minus k over 2 times guess. Figure 3-7 contains code illustrating how to use this method to quickly find an approximation to the square root. With comment Newton-Raphson for square root, and comment find x such that x to the second power minus 24 is within epsilon of 0, and epsilon being defined as 1/100th. So we're trying to approximate the square root of something by finding a number that, when squared, if we subtract the number for which we're finding a square root, is, it's going to be within 1/100th of being equal to this number after it's squared. So that means that we've found something very, very, very close to the square root. Anyway, does that make sense? It's okay. It's still okay if it doesn't. Okay, epsilon set equal to 0.01, guess set equal to k over 2, and then while the absolute value of guess to put to the second power minus k is greater than or equal to epsilon, then we will update the value of guess equal to its own current value minus guess squared minus k divided by 2 times guess. Finally, we will print the string square root of followed by the final value of k followed by the string is about followed by the final value of guess. Finger exercise. Add some code to the implementation of Newton-Raphson that keeps track of the number of iterations used to find the root. Use that code as part of a program that compares the efficiency of Newton-Raphson and bisection search. You should discover that Newton-Raphson is far more efficient. Alright, this is the last bit of it. Terms introduced in chapter. Decrementing function. Guess and check. Exhaustive enumeration. Approximation. Total ordering. Bisection search. Successive approximation. Binary numbers. Bit. Switch. Floating point. Significant digits. Exponent. Precision. Rounding. Newton-Raphson. Polynomial. Hell. Coefficient. Degree. Root. And here's the footnote I was talking about. If you haven't previously encountered polynomials or derivatives, you might find this brief section slow sledding. It is self-contained, so you should be able to work your way through it. However, if you choose to skip it, it will not pose a problem later in the book. Do at least give it a try. It's a cool algorithm. I just want you to know I categorically rejected the suggestion to give this a try.